All right, we're live. Thank you everyone for coming to STEM Fair today. It is my pleasure to welcome you all to the 2021 Virtual STEM Fair. It is incredible that we are able to host panelists and attendees from all around the country. Over the course of this week, you will have an opportunity to hear panels discussing a wide range of STEM areas. It is amazing to see what science can do, from creating a COVID vaccine in record time to the Perseverance rover on Mars. Before starting, I want to say thank you to the amazing, excuse me, to the amazing team that helped organize this event. As I mentioned earlier, this entire week is full of panelists from many areas of science. Last night, we heard from our keynote speaker, Dr. Gupta, and the biology, medical, and chemical panelists. Tonight, we will hear from our lightning talk speaker, India, followed by panelists from astronomy and physics. Tomorrow is the environmental science panel, followed by the computer science panel and robotics panel this Thursday. On Friday, we will host the engineering panel, followed by the college showcase panel. I want to encourage everyone to come to all the panels. These panels cover a wide range of topics, and you never know what you might find. You can go to our website and join through the event links there. Recordings of all the sessions will be available on our website at the end of this week. After each panel, including today, students are able to engage with panelists by asking them questions. You can ask questions to the panelists by using the Q&A feature. To access the Q&A feature, you should see a chat bubble button with a question mark. If you click this, you can type your questions for the panelists. You can also use the Q&A if you have any questions about STEM Fair. Okay, next we have our lightning talk speaker, India. After she gives her talk, we will have the Q&A. Without further ado, please welcome India.
Hi everybody, it's great to be here. I'm going to share my screen real quick. Okay. Hi, so my name is India Balalad. I'm a senior at Yale University studying physics and philosophy, and today I'm going to talk to you a little bit about my research. So this talk is entitled How to Reconstruct a Higgs Boson, and the long form of that title is Multivariate Mass Reconstruction Techniques in a Search for a Higgs Boson Produced via VH Higgs to Tau Tau and Atlas Run 2 at CERN. So that title was a little bit of a mouthful, and so I'm going to break it down as a way of outlining what this lightning talk is going to be about. First, I'm going to talk about what the standard model of particle physics is. Then I'll move into what the Higgs boson is, why we care about it, why we want to investigate it, how we investigate it. So that's namely, what's the Atlas experiment and what is the Large Hadron Collider. And then I'll focus in a little bit more explicitly on what VH Higgs to Tau Tau means and why we should care about this particular way of seeing the Higgs boson. And then I'll finish with my contribution to the analysis, which involves something called multivariate mass reconstruction techniques. Okay, to start off, what's the standard model? The standard model of particle physics is the current working theory of the fundamental constituents of matter and the four fundamental forces that govern their interactions, namely the electromagnetic force, the strong force, the weak force, and gravity. Gravity doesn't really fit in, but that's not really the point of this talk. So broadly, we can break down the fundamental constituents of matter into fermions, which are the building blocks of matter, and then bosons, which broadly are the particles that mediate those interactions. The standard model is an incredibly successful theory, but it's also an incomplete one. We still have core questions about the nature of gravity, dark matter, the domination of matter over antimatter in the universe, and up until 1964, the standard model had essential asymmetry concerning the central particle of the Higgs boson. So what's the Higgs boson, and why do we care about it? So up until 1964, there was a central problem with the standard model, namely, why are the gluon and the photon, the bosons that carry the electromagnetic and the strong force, massless, while the W and Z bosons, the bosons that carry the weak force, massive? So you might wonder why this is even a problem. Well, symmetries in particle physics are incredibly important. As was first proved by the physicist and mathematician Emmy Noether, symmetries are often evidence of important conserved physical quantities. In the standard model, we make extensive use of a particular kind of symmetry called local gauge invariance, meaning we can exploit a redundancy in the math and how we express different realms of the standard model, and that redundancy results in the predictions of the bosons of the mediating particles of the forces. Adding mass breaks the symmetry in a fundamental way, because now we have terms that we cannot cancel. Before 1964, this asymmetry had physicists wondering if gauge invariance was no longer a useful tool, or if there was some other way to explain this behavior. Enter the Higgs mechanism. The Higgs mechanism was proposed by 3 independent groups almost simultaneously in 1964, led by Francois Englert, Robert Brout, and Peter Higgs. It theorized a pervasive field throughout space-time. the more particles interact with this field, the more massive they are. This is often described as being in a vat of molasses. The more you interact with the molasses, the more you're slowed down by it. The heavier you are, the more massive you are. Adding this term to our standard model equations imply that there was some point early on in the infancy of the universe where the universe cooled to a critical temperature and this field spontaneously changed, allowing the W and Z bosons and potentially also the fermions to acquire mass. One thing I want to emphasize here is the standard model is not a single theory. It's a patchwork Rube Goldberg machine of three central theories, namely quantum electrodynamics, quantum chromodynamics, and electroweak theory. Adding the Higgs mechanism is like adding WD-40 to this kind of a machine, and as these different realms of the standard model churn this mechanism through them, we're able to reproduce the bosons we expect to see, massive and massless alike. A note about the Higgs mechanism, nobody really believed it when it was first published. It got rejected from physical letters as being not relevant to physics, and that's because it fixed a mathematical problem, but at the expense of predicting an entirely new field. Luckily, there was a way to look for evidence of this entirely new field, namely an excitation of that field, a particle named the Higgs boson. So how do we even begin to look for this? Well, that brings us to ATLAS and the Large Hadron Collider. So I'm going to play this on 2x speed because the Large Hadron Collider is a huge underground particle collider in tunnels beneath the city of Geneva, Switzerland. I hope this animation is working, but it shows us what it looks like to be a proton that's being accelerated through these tunnels and then smashed together. We'll watch and we'll go inside here. So in the LHC, these collisions are the debris that comes out of these collisions is completely surrounded by a series of machines called the ATLAS experiment pictured here. In the LHC, these collisions are happening on the order of 40 million a second, which is pretty wild. So what is that machine actually measuring? ATLAS is composed of nested detectors, where we can measure the literal geometric position of the particles, their momentum based on how much their paths curves in response to giant toroidal magnets that surround the experiment, and then their energy based on what they deposit in special materials called calorimeters. Each layer can stop a different kind of particle. As you can see here, we have the photons and electrons, muons, neutrons, and protons all can be stopped by the ATLAS detector. All right, so back to the Higgs. In 2012, something really remarkable happened. As tons and tons of particle collisions were being observed, physicists began to notice a statistically significant divergence from the theory, a bump in the mass reconstruction that corresponded to a particle predicted by the Higgs mechanism in the right mass range as the Higgs mechanism proposed by Brout, Ungler, and Higgs. The blue line represents data of the standard model behavior without the Higgs, and the red line represents what we saw, the little bump corresponding to the fact that we saw a Higgs-like particle. So you might have noticed I just said Higgs-like particle. I didn't say we discovered a Higgs boson, and that's really important. Just because we saw a particle in the right mass range is the same mechanism predicted by the Higgs mechanism as the one that was proposed by Higgs, Brown, and Ungler, doesn't mean we actually saw the exact particle that they predicted. Nowadays, the LHC, the Large Hadron Collider, spends most of its time characterizing in detail everything it can about the Higgs boson to see if it really is a standard model process, or if it diverges in a way that would be evidence for new physics. Operationally, this means exploring all the combinations of the way that the Higgs can be produced, pictured here, combined with all the ways that it can decay, pictured here. So I'm going to zoom in on one particular decay channel. That's when the Higgs is produced in association with a W and Z boson, as I mentioned before, and then decays to things called tau leptons. So why should we care about this very particular decay? Well, the energy the LHC is currently operating at, R decay, the one pictured in this box right here, is the last one yet to be definitively observed. And in this no stone left unturned approach of the LHC, it's worth checking for completeness' sake what this decay channel looks like. But also, the tau channel is interesting because within their subcategory of particles called leptons, they are the heaviest. And the Higgs mechanism does this thing called coupling, where it cares about mass. It will decay preferentially to heavier particles. So the taus are interesting because they are such a massive particle. So who's actually doing this analysis? This is the team at Yale who I work with. I've worked with Sarah, Gianni, Marielle, Emma, and Claire for quite a while, and I'd be happy to talk about working with them in other projects. So who are the players in the search? So first we have these two quarks that come in from colliding protons. This is one way that the decay channel can happen. I've picked this one example for simplicity's sake. So the two quarks collide and then they produce a Higgs boson and a Z boson. The Higgs boson will then decay into two particles called tau leptons, which then through a W boson will go on to create electrons or muons, electron neutrinos, muon neutrinos, tau neutrinos, and things called pions. So So the presence of these fundamental particles called neutrinos is actually what makes this decay especially challenging to observe. So the problem with neutrinos, as you might have remembered from before, when I was outlining all the different particles that Atlas can stop, neutrinos are not one of them. That's because neutrinos are extremely small fundamental particles that interact via the weak force, which, as you might guess, is very weak, and it passes through neutrinos pass through most matter like they're nothing. If you want to directly observe neutrinos, you have to build these huge, big, sensitive, really beautiful detectors like this one, Super Kamiokande in Japan, in hopes of forcing and observing a neutrino interaction with everyday matter. Atlas just isn't built to see these particles. And as you can guess, this is a problem for us, because in order to observe the Higgs and determine whether or not it's a standard model Higgs, we have to be able to reconstruct its mass. And to do that, we have to be able to reconstruct the mass of its daughter particles. But now, with neutrinos, we have daughter particles we can't see going off in directions we don't know, carrying off energies we don't know. So the problem has now become, how do you do a good reconstruction when you don't have all of the information? The direct credits on this go to my grad student coworker, Marielle, but as you can see, in physics, as in art, there are good restorations for missing information, and then there are also very poor ones. And this brings me to the last section of my lightning talk, which is what is a multivariate technique and how does it help us? So I'm not going to have time to really cover this tool in the detail that it requires, but in brief, we can relate the missing energy in the event to the mass it should sum to. And don't worry too much about understanding what each of these equations are. The bottom line here is that we have 4 equations that can relate the missing energy and the mass of the taus, what everything should sum to different kinematic variables. The problem is we have 4 equations and 6 to 7 unknowns within those equations, meaning we're going to have 2 to 3 variables that we cannot solve for directly. So this is what we use the MMC for, the missing mass calculator, which is a multivariate tool, which just means that it examines all the possible ways that these multiple variables interact with each other and all the possible combinations that they could to make as good of a guess as possible. My contribution to the analysis has involved generating these things called probability density functions, which take information from Monte Carlo simulation of what we think this particle decay should look like, combined with actual data from Atlas from similar but slightly different production and decay channels, and creating these distributions that we will then feed to the MMC, which encode the most likely ways that these particles are going to behave based on other information that we know about them from classical physics. So in conclusion, the Higgs mechanism helps explain essential asymmetry in the standard model, namely the mass of the W and Z bosons, while preserving an important fundamental property called local gauge variance. And the discovery of the Higgs boson in 2012 was a really big deal, and is worth exploring in its entirety to see if it fits with the predictions of the standard model, or if it's part of some larger, crazier, unknown phenomena. The particular decay channel I work on, VH Higgs to tau, is a worthwhile but challenging decay channel that has yet to actually be definitively observed. And it hasn't yet to be definitively observed because it's so difficult because of the neutrinos in our decay. So in order to handle these neutrinos, we use Monte Carlo simulation and multivariate tricks to make as good of a guess as possible. So I'd like to thank all the following people for making this research possible. And I'd also just like to add, if any of you all have any questions about this research, about physics, about Yale, also about philosophy, that's my other major I spend a lot of my time thinking about, please feel free to email me. I'm always happy to talk about this stuff. Okay. Thank you.
All right. Thank you so much, India, for that talk. I know you all probably have many questions, and we will open up the Q&A right now. Please keep in mind we will try to answer as many questions as possible. Also, just to reiterate, to ask a question, you should see a chat bubble button with a question mark. If you click this, you can type your question for the panelists. Moderators will read your question. So, India, our first question from a student is, how did you choose which STEM field to enter? For example, why did you study the Higgs boson?
Sorry, my internet just cut out. What just happened? Did we get a question?
So our first question in the chat is, why did you choose to study the Higgs boson?
Oh, for sure. So I have wanted to study particle physics for most of my life. I remember hearing about the Higgs boson when I was in, I think about middle school at the time, and it was probably the biggest physics discovery that I can remember. Maybe the second biggest one was when gravitational waves were detected, but I remember the excitement around it, and I remember how crazy it was for someone to say, oh, we discovered evidence of a particle that is part of a field that gives everything mass. And the concept of studying something that fundamental just like completely blew me away. And also the fact that we could even say that we could definitively say that, I thought was a pretty crazy thing. So I don't know, I had a really helpful, encouraging mentor in physics in high school. He encouraged me to work on this more, apply to Yale. I came to Yale, and I've just been bouncing around different parts of research before I actually ended up with the Higgs boson, where I kind of originally wanted to be anyways. Thanks for the question.
All right, hi, we have another question, which is, what would the world look like without the Higgs boson?
Oh, that's such a good question. Oh gosh, okay, so the thing that I'm still constantly trying to wrap my head around is, so the Higgs boson isn't actually what gives things mass. It's the Higgs mechanism as a whole, and it's the field that things interact with in order to have mass. What would the world look like if there was no field to give everything mass? Probably just a big pulsating ball of energy, although I don't have a great answer. It wouldn't be anything like what we know right now.
Hello, Ms. Balalad. We have another question for you in the chat. What part of your research was the most challenging for you?
That's a good question. I think, well, there's a couple of pieces. It took me a while to get to my research. First of all, I think I had a bit of a fair amount of trepidation about actually contributing to analysis on the scale. The Atlas experiment is composed of like hundreds of institutions worldwide. So there's lots of physicists who are involved, who are professors, who are postdocs, who are graduate students, and I had quite a lot of trepidation about becoming an active contributor to that. But my mentor was extremely encouraging, and just kind of told us constantly that like everybody who we were ever going to work with started out exactly as we were, and you had to start somewhere. I think a more technical answer to that question is, because Atlas is such a big experiment, there are like huge software frameworks already built up in place. So getting used to that and like talking in the language that other people were talking in took a little while.
A question from the chat. For someone who is uneasy about going into the physics field, can you recommend any ways a student can test the waters of the physics field and try to enter it?
For sure. I'm a big proponent of just like trying by doing. I think when you go to either college or honestly in high school, most professors are eager to hear from new students who are excited about their research. And I think it's really hard to figure out if you're going to like it, if it's going to be a good fit for you, unless you actually try it. And I think there's a lot of I don't know, anxiety around actually trying it, but quite honestly, professors are not going to expect you to do anything you can't already handle, and they're going to help you. If you have a good professor, that's key. If you find a good mentor, they're going to help walk you through what you need to know. And just like getting your foot in the door and trying it, it's easier. It's better to know earlier if you don't like it, and then you can try lots of other things. But I would just say, as much as you can, like, I don't know, it's scary, but like cold email a professor and try to get some work in.
And in the chat, we have someone asking, how has your philosophy influenced, like how has your philosophy influenced your study of physics?
Yeah, big time. I'm a big fan of integrating the humanities with the sciences. I think it's great for both fields. I think it's important to both fields. And I actually came to physics through kind of a philosophical framework. My high school mentor was also a philosophy teacher. And every time there would be new discoveries, we'd kind of go over the implications of like, what does it mean to like talk about a particle? What is like, is a particle like kind of like a billiard ball, like we seem to talk about it in class, or is it something more complicated? Is it like a wave packet? That seems kind of crazy. And I think there are like ways that all of these kind of play out in the realm of philosophy, and there are philosophers of science who are really interested in like, when you get more advanced into physics, like what quantum means for different ideas of causality, like what it means for two things to be the same thing. And I think that there's quite a lot of like lack of communication between the two, so that there's a lot more that could be gained from both physicists trying to think more philosophically and philosophers trying to think more physically. For my own immediate research, I find the Higgs boson fascinating because I mentioned this briefly, but it really was this like mathematical property that someone was trying to fix, and then it ended up predicting the existence of an entire physical field that you could observe, which really makes you wonder about like the structure of the math and like how real and like how much reality is encoded in something like math, and how did we even get math in the first place. But I don't know, that was a long answer, but it's kind of in everything that I do. I think it's really cool.
All right, and then we have another question, which was, in your academic life in general or with your research, what were some obstacles that you faced and how did you overcome them?
I mean, there's always quite a lot, but I think like probably the biggest one was, well, there's two. I think probably the biggest one was handling the transition from high school physics to college physics. I think that was a big transition for me. I think it came with a lot faster of a pace, and then a lot faster of a, oh, how do I really deserve to be here if I'm struggling with this problem set? Like, do I really deserve to be here if this isn't coming easy to me? Which is, I just learned was completely fake. Like, I joined a women and underrepresented gender minorities group in physics pretty soon after I came to college, and it was the best thing I could have done for my psyche, because it quickly became apparent to me that every single person was struggling on the P-sets, even if they didn't say that they were. If they didn't say that they were working on them together in secret and not telling me. Like, it's just people don't like to say when they're struggling, even though everybody constantly is. So like I remember a grad student and I brought her my problem set for my intro to physics class in my freshman year. And it was the first problem, and I had like so much embarrassment over the fact that I couldn't do the first problem. And she and I, who was a grad student, and then her partner, who was also a grad student, spent like an hour on a whiteboard trying to figure it out. And it's just because it's hard. Like, it's always hard, but like you work with people, and that's what's different about college physics. You're constantly working with people, and that makes things a lot easier.
So we had another question. What advice would you give a high school student who's passionate about physics?
Yeah, go for it. I mean, like, I think there's a weird like pedestal feeling to physics, like, oh, you can't touch this unless you've done X, Y, and Z things. But honestly, if you're excited about it, just go and do it. Like, professors are excited to be working with people who are excited, and like, there's going to be a lot of ways that you can use physics, even if you don't really feel like you want to go into academia. There's a million different ways you can keep pursuing that interest. So like, I think practically start taking classes earlier. I wish I had taken more math. I always wish I had taken more math. Take a bunch of math. That'll help you all the time. And like, look at the professors and see the research that they're doing. Or honestly, it doesn't even have to be professors, but look for people who are doing cool research and email them and just express your excitement and see what they have to say.
Okay, we have another question from the chat. What is the best part of working in your field of education?
I think I've been quite lucky at Yale to interact with the people that I've interacted with. In all of the research groups that I've been in, I've been with a cohort of really just excited people. And that's kind of happened regardless of the research group that I've been in. Like, I think physicists are like, I don't know, there's something about like someone will come and give a talk on their research that they spent the last 3 years working on, and everybody is so completely enthralled by like, what could this possibly mean for my research? What could this mean for like the manifold of reality? And they just want to know, and they just want to ask all these questions, and everybody's like, I mean, of course you can be in places that are less cooperative, but the places I've been in have been very cooperative and very eager to help you like understand all those things that everybody else is trying to understand. Everybody just is just excited to learn all the time, and like, I don't know, there's something kind of beautiful about like building these huge machines and then using them to try and figure out what's going on with the world. And I don't know, I think all scientists in general have a bit of a romantic flair to them that they wouldn't admit to, but I enjoy that.
Another question. What are some common misconceptions that people have right now, and how do you wish these misconceptions could be like kind of combated?
Misconceptions about what? About physics?
About your field of study. So yeah, physics. The physics field.
Okay. I think the biggest one that I definitely had was that there was one way to do it. Like, even within physics, so I don't, this isn't a totally fair way to characterize it, but like there's one way to divide up the world of physics, physicists into like experimentalists and then into theorists. And I think everybody thinks that being a physicist is being a theorist and like working on a blackboard and like by yourself in a basement and like deriving equations, but that's kind of not what the practice of modern physics actually is, especially if you're more on the experimental side. I mean, even if you are on the theory side, you're going to spend a lot of time on like working on computer simulations in groups and at whiteboards, but like in groups. But on the experimentalist side, like you're going to have a lot more of like an engineering and like software engineering flair to it, which I think is a lot of fun. It's like problem solving and like working with like literal machines. Like you have to figure out like the refractive index of a certain gas in order to understand how your detector works. And you're going to be like drawing diagrams all day and like solving puzzle after puzzle after puzzle. And like that's not even like half the way that physics works, but it's like there's already so much variety between those two. So I think it's good to know like physics later on, like in the career of being a physicist, is quite a varied occupation, and I think that makes it kind of exciting.
We have one question. What about the pursuit of Higgs Boson makes it one of those few scientific endeavors that seems to capture the prolonged interest and imagination of the general public?
That's a great question. I think that happened for a couple of reasons, and this is very much just my opinion. You all should research this on your own time and not just trust me. But like, the Higgs boson was like sensationalized. It was international news everywhere, and I think like part of it had to do with the fact that it was one of the biggest discoveries that we'd had in a long time in particle physics. Like there was not a lot happening beyond what had happened in like the earliest 20th century. So when the Higgs boson was discovered, it was like big deal at a big super collider. Like these things are huge and expensive and like take up a lot of people's brain space. I remember there was this one crazy article that was like, the Large Hadron Collider is going to open up a black hole and you should all be worried, which was just not true, but the public got really worried about it. And then I also think like in my opinion, the Higgs boson is really cool. It's like 100% worth studying. It's sort of Higgs boson-like particles. It's part of a lot of different theories. But I also I think it's also been kind of hyped up in a way that kind of isn't fair. Like, I think colloquially, the Higgs boson is known as like the God particle, which I think every single physicist I've ever met hates that name because it's both kind of premature. We're still like looking into the Higgs boson and trying to understand like what it means for physics, what it means is for the field, for the mechanism. Are there other things going on with the Higgs boson? And also the idea that like the particles responsible for endowing mass isn't exactly accurate, like it's more the field. But like, I don't know, I'm all for public support of science and like public education of science. I think that's always a good thing. But I do think the Higgs kind of picked up quite a lot of like misinformation, but also public excitement. Maybe those two things kind of come together sometimes. But yeah, it got my interest, so.
All right, and then kind of similar to what you were talking about before, but what is something you learned that really blew your mind while at U?
So many things. I think the one that's coming to mind is like the further you go in physics beyond like your high school classes, the more they'll tell you, oh, everything we taught you before is like the wrong way to think about it. It's actually completely different. Like we need to like redo it, and we'll show you a much more abstract but simpler and kind of beautiful way to think about it. And like for me, the first time that happened was in my like college level classical mechanics class, where my professor put on the board this like crazy problem that would have given me such a headache in high school. It was like a series of like springs that were all attached in a circle that was like rotating somewhere, and he was like, tell me about the velocity of this one part of the spring, and all of us were like freaking out because we couldn't figure out how to do it. And then he said like, oh, so what's really interesting, this is actually a really simple system if you don't think about it in terms of classical mechanics, but you think about it in terms of these things called Lagrangians and Hamiltonians, which I won't go into right now, but broadly, they're like a much simpler way to think about mechanics that all completely involves energy conservation and minimizing, taking the path of least resistance, so to speak. And it made the problem doable in like, I don't know, like 20 lines instead of like 3 pages. And it made me just completely shocked that like you could understand this really complicated phenomena in a way that like was actually not too hard to get a grasp on, and like came out of this concept of actually Emmy Noether's theorem was a big part of that, who I mentioned before. She's a really cool mathematician.
And the last question to wrap this up is it difficult to be successful in the physics field? And do you only get paid well if you're at the top?
Well, you know, once I leave college and I try to do it, but I think the thing that's hard about physics is like, if you're just looking at it from an academia perspective, if you want to stay in academia and be a professor, then that's quite competitive. Like getting a professor position is quite competitive, as it's going to be for most professorships. But the thing I think that's good about physics is like, that's not the only thing you can do with your degree. Like there are plenty of really cool jobs going on in industry. You could work for NASA. You could work in like the technical side of CERN. You could work as a research scientist at a national lab. I don't really know how to answer the salary question, except that you're definitely going to get paid better if you work in industry versus academia. But at least personally, for me, the trade-off then is having less control over your research if you're in industry versus academia. So I don't know, it varies from person to person and like what niche within physics you decide to take.
All right. Thank you so much, India. That concludes our Q&A. Next up, we have our panelists for the Astronomy and Physics panel. Each panelist will give an introduction of themselves and their research for about 5 minutes, followed by an open Q&A. India, you are welcome to stay for the panel. Our first panelist introduction is Boris, so please take it away.
Okay. Hello, everybody. My name is Boris Blinov, or rather, my name is Boris Blinov, because I'm originally from Russia and I got most of my education, except for the very last step, the PhD, in Russia. So actually, even not in Russia, in the Soviet Union, the country that no longer exists. So in a sense, I came to doing science, and specifically physics, maybe in part because of the way the education worked back there. There was a lot of opportunities for students in high school and even before high school to participate in activities outside the classroom. We had these Olympiads, physics and chemistry and biology, and English language Olympiads, where students can compete, and we would basically meet people of common interests, and that really helped me grow and realize that physics is probably what I really want to do. So currently I work, I'm a professor at the University of Washington, and I work on quantum computing and quantum information, the experimental side of things. So we're, it's an enormous undertaking that is being pursued by many groups in many universities and industry, and we're doing our little thing, trying to help build this new device. That's my introduction. Thank you.
Thank you so much for that introduction, Boris. Our next introduction is from Derek, so please take it away.
Hi, everyone. So I'm actually going to show a couple of slides, and then I'll give my origin story at the end. Okay, so excited to be here today. So what I work on is plasma physics and fusion energy. So you might be familiar with plasma as being the fourth state of matter, solid, liquid, gas, and plasma. And so these materials are composed of ions, electrons, and atoms at very high temperatures. And what's important about them is that they're capable of exhibiting collective behavior. And so what that means is that both electric and magnetic fields can be used to influence the plasma behavior. And so here's a couple examples of the types of plasmas in nature and also man-made, in the sense that you have that plasma ball that everyone played with as a kid. You have the bigger version, which is the sun. Lightning is another example. And then this is actually a tokamak plasma, which is what we use to actually pursue nuclear fusion. And so we can use heavy hydrogen to generate fusion energy by creating artificial stars inside of machines. And as cool as that sounds, it actually is real. And so there's hundreds of machines around the world that are all focused on making fusion a reality. So this operates via E equals mc squared, Einstein's famous equation. And you make excess energy to turn into heat and electricity. And what's really cool about this is that even though it's nuclear energy, there's no risk of meltdowns and no long-lived radioactive waste. So you get rid of those two negatives of fission power. So the goal here is to produce fusion reactors that can provide a clean, carbon-free, and high power density energy source to work together with wind and solar to provide a complete green energy solution for the planet. And so my work is focused on how to make fusion commercially viable. So there's actually a host of private fusion companies in Washington and also a bunch of other ones in the US and also abroad that are all looking to bring fusion online in the 2030s. So this is really good timing for exciting jobs after finishing college. Oh, and then just for a bit of my origin story here. So my educational background, I started as an unofficial science nerd in middle school, as most of us did. I was in the IB program for high school in Orlando, Florida. Then I got my undergraduate at MIT. I double majored in nuclear science and engineering and in physics. Then I continued on to get my doctorate at the University of Washington in aeronautics and astronautics with a focus on plasma physics and fusion. And there's actually a website called the University Fusion Association that has a list of all the different universities in the US and abroad that have plasma physics and fusion programs. So excited to be here today.
Thank you so much, Derek, for that introduction. Our next introduction is from Natalia, so please take it away.
Hi, can you hear me?
Yep, all good.
Okay. Well, hi, my name is Natalia Tapia. First, I want to thank the organizers for inviting me to this event. Well, I'm a postdoctoral associate at a university called Virginia Tech. I work in research in particle physics, more specifically in dark matter, neutrino physics, cosmology, and a bit of gravitation. I basically try to understand what dark matter is. If you haven't heard what that is, if you look at the universe, for example, and what you can see from the universe, what you actually see is only 5% of the total energy content of the universe. 5 times larger than that is dark matter, and the rest will be dark energy. So actually what we understand from the universe, what we see, it's only a 5%. The rest is dark matter and dark energy. So we try to understand what is there in the universe that we cannot see, but we see its effects on planets and galaxies, for example. And also in case of dark energy, that contributes to how the universe is expanding. I also work in neutrino physics, as I think Dr. Balalad mentioned. Neutrinos are very tricky particles, very difficult to see in terms of experiments. But it's very fun to work in this kind of research. In the beginning, I wanted to be an astronomer, actually. I was born and raised in Chile. I don't know if you have ever heard of that place. It's in the very south of the continent, in the capital, Santiago de Chile. I did my undergraduate and my PhD at the University of Santiago de Chile. And during my PhD, I had the opportunity to travel to Germany for an internship or an exchange at the DESI, which is a very known research center in Hamburg, where you can work in particle physics or string theory, things related to that. Also, I had the opportunity to go to Montreal to work there in gravitation. And finally, I ended up here for my first postdoc. So I'll be very happy to answer any questions about dark matter or particle physics that you might have. And thank you again for inviting me.
Yes, thank you so much, Natalia, for that introduction. And India, for those who may have missed it, do you want to introduce yourself once again real quick?
For sure. Hi, everybody. My name is India Balalad. I am a senior at Yale University studying physics and philosophy. If you were there for my lightning talk, you'll know that I study particle physics. I have done mostly experimental particle physics, but I'm moving into more theoretical and phenomenological particle physics. I was born in Boston, Massachusetts, and very quickly moved to Washington, D.C. And I've jumped all around in terms of my physics research. And as I am currently about to start a PhD program I'm still deciding where I'm actually going to go, but I'm about to start my PhD program. But in terms of my actual research, I've kind of been all over the place. I did a little observational astronomy, actually in Santiago, Chile, Dr. Tapia, that's very cool. And did some observational astronomy, and then I worked in more of an instrumentation engineering work for a year. I did looking at the properties of these materials called liquid simulators, and learning my way around a machine shop, how a lathe works, how a laser cutter works, how you design an experiment top to bottom. And then I transitioned into closer to what I do now in particle physics. I worked at Fermilab, which is a national lab in Batavia, Illinois, for a year or so on an experiment called MUDE, which looks at physics beyond the standard model, still particle physics. That was also more on the software side, and also gave me a taste of what it's like to work in a large collaboration in particle physics, which I very quickly fell in love with. And then within the last year and a half, I've transitioned to working on the ATLAS experiment at CERN, which is based at the Large Hadron Collider in Geneva, Switzerland. I've done a lot of different things for the ATLAS experiment, not the least of which working on the particular hard to observe decays of the Higgs boson. Yeah, that's me.
All right, thank you everyone for those introductions. We will now transition into the Q&A portion. We received some questions when you registered, so we will ask those first, but please still ask questions in the chat. We will try to get to as many questions as possible. Our first question is for any panelist. What is one part of your job that surprised you or that you didn't know when going into physics?
I could comment on that. There's a lot that in addition to the physics, that you have to do to make everything work. So, you go into it thinking that you're going to spend 100% of your time doing physics, but in fact, there's a lot of extra stuff that goes along with any job. So that's like, for example, it takes a long time to write a really good paper. And when you get all the results, then you have to put that into a publishable form. Do not underestimate how long it takes to make good figures. That's what I would contribute.
If I may say something, for example, in particle physics, I work in theory, but I had never in mind that it will involve so much computation time. I was not a friend of programming or coding or anything like that. And I've been forced to learn, which was a bit terrifying at the beginning, but when you start learning, and it's very satisfying to see that you can learn these things that seem so difficult and terrifying. So it involves much more than what you have in mind. It's not only looking at books or I don't know. It's much more, and also writing papers takes a big time of your research time. I would say the most important portion of time is writing papers.
Maybe I could say a couple of words. So I'll come from a more distant, maybe perspective, more senior perspective of teaching physics. So when you become a professor, you actually end up teaching the same courses that you took while you were a student. And what I hadn't realized until I started teaching physics is that I really didn't understand those things that I learned. So it's kind of interesting, unexpected.
Okay, so
Oh, sorry.
No,
I was
you
just
can.
gonna say, I'm quite obviously very early on in my career, but I think even so far, what I've been surprised by the most is just, I mentioned this a little in the Q&A previously, but how many different paths within physics there are. I think I had a very narrow conception of like what it would mean to be in physics, and it was like very narrow, like chalkboard deriving equations by myself in a basement, and that's just quite honestly not what it is. Like echoing what Dr. Arellano said before, like quite a lot of computation. There are people who spend all their time in instrumentation, which is really cool, and like people who, I think the definition of being, what you could encompass in being a physicist is actually quite a lot of different people. And I think it's been exciting to discover all the different ways that has manifested for people.
Okay, so if no one else has anything to contribute to that discussion, we have another question in the chat. What would you recommend for a student interested in astrophysics? And this is for any of the panelists.
What would you recommend in terms of what?
I think for like a student who is trying to pursue the education in astrophysics, study of astrophysics, what would you recommend?
Well, I would say the nice thing about physics is that it's universal. So when you learn the fundamentals, which is what you'll start with any course, then you can specialize into any direction you wish, whether it's particle physics, plasma physics, or fluid mechanics, or astrophysics and cosmology. And so I think, more important than just going into a specific direction right out of the gate is to really sample a lot of different types of classes when you enter your course, and then figure out what really gets you interested. Because that interest and that passion for whatever you're pursuing is what's going to get you through the ups and downs that is the challenge of getting through a physics program. But it also makes it extremely rewarding if you're doing what you really love and find interesting.
I think it's specifically about astrophysics. So for example, I wanted to be an astronomer or an astrophysicist when I was, 15. But when I entered the university in my country, I didn't have the score needed to study astronomy in the university that I wanted, or the place that I could have gotten a scholarship, for example. So I entered studying physics engineer, and I didn't finish the engineering part. I only got the bachelor, and with that I entered to the PhD program, and I ended up working in astroparticle physics, which I do not regret. I think in the end that's what I really wanted to do. I might be wrong, but astronomy and astrophysics involved more data and observation, and what I really wanted to know was the fundamental physics, I think, behind this, like the Higgs boson or neutrino physics or quantum electrodynamics, understanding the basics of particle interactions more than, well, looking at the stars is always nice, but I think what I wanted to do is to understand things, and maybe as Derek said, is keeping an open mind. That in the end, maybe your path will go in the way that you really want, even if you don't have the chance maybe at the beginning, but I don't know, somehow things work, I think.
All right, unless anyone else has anything else to add, let's move on to the next question, which is it hard being a woman in STEM, and like, what is it like?
Should I start? I think it is as hard as being a woman in many other subjects or fields. I can only talk from my personal history. For example, I was the only female student in the PhD program in my generation, and that made things a bit more challenging, I think, that for my classmates, because most of the time when you should be working in a group, I was working alone. But that's not the case for everyone, I think. That was my specific case, that maybe my classmates or the society where I was working was not with me in that thing. But I have to say that sometimes I got much more help from male professors than female professors. My supervisor was a big part in me being able to finish my PhD program. Without his support, I wouldn't be here today. So I think it depends on the people that you choose to work with. You have to choose a good advisor, someone that you can talk to, not only about physics, I think, because your life is not only your work. You need to have space for other things. But you may face things that maybe as a male student you wouldn't see, comments and things that, yeah, it might be a bit more challenging, but that depends on any case, I think. So I just can say that it is not always the same, and you can be much more lucky maybe than what I was, but you don't have to lose hope. I think it depends on many things, and things are very different now that it was when I was starting my PhD. So I think you just have to try, and you can find a lot of people that will want to help you if you have difficulties during your time in research or studying.
Yeah, I can speak to this a little bit too. I've had, I think, a pretty varied experience in terms of being a woman in physics and in science, and I actually had a similar, similar problem in that most of the obstacles that I faced tied to, I think, being a woman were more like undertones, and they were like overtly insults or something like that, like exactly like, oh, I'm going to work more alone than I'm going to work in teams because people aren't going to necessarily reach out to me and form a group, or I'm not going to be asked first to solve a problem versus someone else who, like versus my male classmates who you'd be asked to solve a problem. I think this intersects with a lot of other things besides gender, but I think like the biggest thing if you want to stay in physics is about finding the community that's going to support you through that, because if you have a strong knit community of whatever it is your identity group is. For me, it was the Women in Physics group at Yale. Those were the people that I went to work on my problem sets with first, and they were excited to work with me and like excited to ask the questions and the problem sets that are going to get you curious about bigger things in physics later on. That's like as much important part of solving the problem sets is like actually solving the problem. So it's like it's finding a community of peers who can like help you with the day-to-day support that maybe you're not going to get from the start. And then also I've had a couple different mentors, but I tend to gravitate actually towards female mentors because I don't know if that's just a personal thing, but I felt quite supported in those environments where it's not, I'm not an exception to the rule, if that makes any sense. Like, I think this is, I don't know if this is entirely coincidental, but my current research group is led by Professor Sarah Demers, who's a woman, and most of our team is women. We have one postdoc, Gianni, who is a sweetheart, and I care about him quite a lot, but we're pretty much all women, which is a really different way to do physics than I've done before, but it's been really encouraging and supportive, and like has also helped me with exactly like what you said, Dr. Arlono, with like understanding how to balance physics with other parts of your life, because being a physicist doesn't mean it has to be completely encompassing of everything that you do, and I think it can feel a little bit that way if you already feel like you're starting from behind. So just surrounding yourself with people who like can affirm for you that both you're supposed to be here, you deserve to be here, and also that this doesn't have to be your entire life for you to deserve to be here is really important.
All right. So we have a question for the general audience that, or the general panelists, sorry. What steps did you take when you were younger and to get to the point that you are today?
So maybe I can jump in. Okay. I'm not sure if I'm live right now.
Your could you please turn your camera on? Yeah.
Right. Okay. The icon was unmuted, but is it working now?
Yeah, we can hear you, but your camera's not on.
It's weird. It's probably just some delay, because the green dot is on, but I don't think. All right.
I see your camera.
Okay.
I can see you too.
Okay. So when I guess I realized that I want to do specifically physics was fairly early. Maybe I was maybe in the 6th grade, maybe 7th grade out of 10 grades in the Soviet Union. So I had still some years to go. And so I basically started reading all I could, all of the textbooks that, textbooks really, that seemed appropriate and for my age and also interesting. But I mean, maybe those steps aren't necessarily applicable in this country, in the current situation, or the way the educational system works here. But I think, to me, as I already mentioned, the biggest probably deal was actually networking with people like me, other students at the same stage of their career, meeting them through various, maybe not panels like this. We didn't have virtual meetings and such. The meetings were in person, but meeting them, discussing what physics is about. You know, we didn't know very much, but we tried to learn, and deciding on this path.
All right. I can jump in too real quick if there's interest. So where I started in science is that I actually got quite interested in meteorology. I grew up in Florida, and so when I was a kid, Florida got hit by a bunch of hurricanes all at once, and that got me really interested in that power, and then also the climate change aspect of it. So I kind of fell in love with that field. And then when I took physics in high school, I really, really liked electromagnetism. I thought that was really pretty. It's a nice central force. The math is really nice. It's not like QCD. And so I was looking for something that combined fluid mechanics and electromagnetism, and fusion is exactly that combination, and plasmas is exactly that combination. So that's kind of how I formed what I wanted to do, and that was actually pretty early in high school. And then since making that decision, I went after it and just kept going at it, and here I am today. And I found that working with a lot of different people from a lot of different backgrounds is instrumental in really building out your experience as a human being. But also it's really important for understanding that there's more than just one way of thinking that's correct. And it just enhances your own sophistication, how you can think about things in different ways, which is how you become a really successful physicist as well. And so I would highly recommend, once you get into college, really go out and engage with as many groups as you can, to really just broaden your scopes and to learn about as many different perspectives as you can. Because once you differentiate, that opportunity isn't quite as extensive. And that's what I wish I did more of in college when I was there.
Thank you for that response, Mr. Sutherland. And we have another panelist joining us. Sanjay, if you'd like to introduce yourself, that would be great. You're muted, Mr. Sanjay. Sorry.
Well, yeah.
Thank
Hello,
you.
everyone, and my apologies for joining late. I had trouble joining because I was using the wrong email address. My apologies. I grew up in India, did my undergraduate education in India, then came to the US in the early 90s. I got my PhD in nuclear physics at Stony Brook. And my interests when I came to the US was to do quantum optics. And then I just drifted and ended up doing nuclear astrophysics. That's as far apart as it can get. And since then, I've gotten fascinated with, a whole lot of problems in nuclear physics, in cold atom physics, in astrophysics. And what I enjoy about theoretical physics is the ambition of it. It's just boundless. You try to connect the very small to the very big, and there's a lot of very interesting complex stuff in between. So we're not kidding ourselves as physicists to think that we can solve all the problems, but we can certainly solve the very small problems and interestingly the very big problems. And that connection is what fascinates me. And my research has largely been driven by this fascination for connecting very large phenomena like core collapse supernova that explode, or mergers of neutron stars that happen in the galaxy, to fundamental physics, to fundamental particle physics, to the understanding of how neutrinos, how quarks, and how nucleons shape these extreme phenomena.
Awesome. Thank you so much for that introduction. We do have one question in the chat. How can physics and other degrees like business, philosophy, or mathematics work together? Any panelist can offer an answer. Yeah.
I can jump on this one quickly for philosophy, because that's the other half of what I study. I think it's incredibly helpful and important to study philosophy alongside studying physics. I actually got into physics through a philosophy mentor of mine in high school, and talking about like the stakes of the big discoveries that were happening when I was in high school. And I think philosophy has a couple of ways that it can be helpful for physics, and also vice versa. I think studying both the history of physics and the philosophical frameworks that physicists and scientists have been working out of to develop their theories is incredibly generative, and both understanding the ways that we currently understand our theories and work within them, and understanding the biggest revolutions that have happened in physics. I think the quantum revolution is particularly interesting to study, the development of special relativity and what it took to shift that framework in both the physics and the philosophy worlds is really cool. This is a side note, but like studying the philosophers who were really influential on Einstein is I think a really interesting exercise, because it's very clear that he had outside perspectives coming in. And I think it was Dr. Sutherland who said before that it's often the outside perspectives and the ways that like change the way that what you bring to understanding physics is what's going to be quite unique about the way that you do your work. And I think that's really important, and especially interesting when you approach it through philosophy.
Yeah, and just to add a little bit in complete agreement, I think that's exactly right. So when I was in an undergrad, I minored in history and I minored in philosophy, because I view both of those as kind of two sides of the coin, because history is just seeing what philosophy did in the past and how it was implemented. And I find that when you wrap physics within those two contexts, it's really interesting. Like the history of physics, how it's guided all of these huge events in history, changed the world, and understanding the big decisions that people had to make, like regarding what is ethical when you discover something new to do and how to use it. And also when you are studying some of this really cutting edge physics like quantum mechanics and things like that, there are some things that you will observe, no pun intended, that don't exactly make sense compared to what you're used to in the everyday world. And so really getting a good philosophical system to underpin how you interpret that information will keep you grounded much more than if you didn't have a system set up a priori. So I completely agree with India there that philosophy I view as the fundamental, not physics. But philosophy gives you the way to interpret what you learn from physics using the scientific method in the human context.
All right, thank you for those amazing answers. And we have another question in the chat. And it is, did you consider other career paths before choosing the one you have?
Maybe I can answer that. As I said before, I think what you do as your work doesn't define your whole life. For me also, I don't know, worrying about climate change or I don't know, the amount of plastic that I produce or animals and things like that. It's very important. I wanted to be a veterinarian when I was a kid, or I don't know, other things. But for example, I cannot see an animal suffer, so I couldn't be a veterinarian. Then I got interested in stars and planets, and then I said, okay, I will be an astronomer. And then I ended up being just a particle physicist, which is not the same, but it's close, I think. But yeah, I mean, sometimes you can be surprised what you wanted to do at the beginning and what you end up doing. And I think maybe related with your previous question, I cannot say exactly how you can relate particle physics to economy, but sometimes in trying to understand a problem, you find yourself going far from where you started. For example, I'm working in something related to dark monopoles, and somehow now I have to learn something about plasma physics to understand more. Or in other projects, I want to learn something about solar neutrinos. And if I want to understand more of the sun, or if I understand more, then I can understand more of the Earth's climate. So then you see how these things that you maybe think are not related at all, you can relate different things. So maybe I deviate a bit of the question, but yeah. Thank you.
I can also jump in, if I may. So growing up, I was actually considering a career of an artist. I was pretty good at it, and probably not as good now, but you know, so around the time that I had to decide whether or not to be a physicist or an artist, a painter, I guess I had a conversation with my parents. My family is actually pretty much all of them are scientists. My mom is a physics teacher, high school physics teacher. My two uncles are physics professors. So I guess there was no kind of art representation in the family. And I basically was convinced that the physics career is what I should pursue, but I didn't give up painting. I continued just painting on my own throughout my undergraduate years. And in grad school at the University of Michigan, I actually took painting as my, what's it called, the breadth requirement for my PhD degree. So that was, and still is, part of my life.
Growing up in India, and my parents were both doctors, and in India, if you don't grow up to be a professional, which is either a doctor, an engineer, or a lawyer, it's because you're not doing so well in school. And if you choose to do physics or mathematics, it's very rare that you would have somebody who's doing it because they're genuinely interested. Maybe 10% of the people would be doing it because of genuine interest. The rest would be doing it because the other options weren't available to them. And so, I had a really great high school physics teacher, and I thought I really liked it, and I was doing it well, as opposed to everything else that I was doing poorly at. So it just led me to think that, if I want to do something well, I must really like it. And at that time, I liked physics. So I continued on that path for many years until, I was about to get my PhD. And I suddenly realized that at that moment that, geez, this is a tough field, and there aren't a whole bunch of jobs to get. But things worked out okay. And my advice to young people who are interested in science is, if you love it, just do it. And everything else will fall in place, because the passion that you have for the topic will propel you to do interesting things. And physics is especially unique because it teaches you how to solve problems. And that's the fundamental basis of physics. It gives you the tools required to solve any problem. And it gives you the framework to think about formulating problems. Most of the time, the most interesting things are in formulating the question. What is the right question to ask? And physics is very unique at this. It is one of the few fields where we keep changing the questions we are asking. And sometimes we change it because we just don't have answers to the questions we asked in the past. We come up with new questions, and these new questions, derive new knowledge, and that can be used in any arena, whether it's business or medicine or chemistry. That's an analytic tool that is very, very powerful.
Okay, so if none of the other panelists want to contribute to the discussion, we have another question in the chat. This is for any of the panelists to answer. What is the best way to set yourself up for a physics degree? And what are some common mistakes you should avoid when first starting?
I mean, I'll let you know later this worked out for me, but on a very practical level, in high school, I took pretty much all of the physics, math, and computer science classes that were available to me. And then in my summers, I looked especially for computer science programs. I did a program called Girls Who Code, which is actually free and phenomenal, which gave me honestly the basis of my Python skills that I've then spent the rest of my physics career so far working in, which was incredibly helpful. And I read a lot. I read a lot of both popular science books, and also tried to read some science articles in high school with the very limited knowledge that I had. But I found a teacher who was particularly excited about the field, who would explain things to me when I ran into questions, and just kept taking as many classes as I could. Because honestly, when you get to college, you're going to repeat them most of the time. Some colleges will let you, if you have AP credits or something, will let you skip your initial requirements. But I found a lot of them require you to take them again, which I don't think is a bad idea. I think it's always good to keep returning to those first things that you're going to keep learning. And then continuing on the computer science side of it, because that's ended up being what I spend most of my time doing.
Yeah, my advice would be to seek out really good teachers. They may not be at your institution, they may not be in your state, but now you have access to the internet. You have some incredible lectures available. There are lecture notes on all sorts of topics. So find people who are able to understand, simplify, and communicate that to you, and that can be a great help. Very often it's hard. Problems seem harder than they should because they're not being well understood. And when you have a person who is able to spend the time required to understand a problem and then simplify it, then it gives you a leg up. So you don't have to make all the mistakes everybody made before if you seek out people who are the lecturers or the teachers who've kind of done that for you, and that can give you a real advantage.
Yeah, I would say too, just a couple things that I wish I did differently. Learn to code. I think it's already been said, but learn to code. Python will be your best friend. It's free. Learn Python. Second thing is do not skimp on the math classes. If there's any doubt that you think, oh, should I take multivariable again or not, take it again. Because all of the fundamental math, the differential equations, the calculus, that is the language of physics. And also take linear algebra for sure. And so if you understand all the math and you really got that solid, physics is so much easier. Otherwise, it's a lot harder. And then I would say too, speaking to first year Derek at college, when you take that exam in that class that's not quite clicking, and it's your first college level exam and you get your grade back, don't freak out. And go talk to others in the class. You'll find out that everyone else failed it too. And then you all work together on your problem sets and you build the knowledge together. And then everyone gets smarter as the class progresses and the scores go up into the final. So they're designed to slap you up a bit in the first year to bring you back down to earth. And then you just come back even stronger afterwards. So don't freak out.
All right, we have another question in the chat, which is, could you guys tell us about the most surprising experiment or project that you guys have done?
Well, I can share one of the most amazing little things I discovered for myself. I mean, it's not something that I definitely contributed on my own, but it was part of the research that I was involved in when I was a postdoc. And we were studying what kind of matter would exist at the highest possible densities. So, and you know, the naive thing that you would think was, you know, if you take matter and you compress it to incredible densities, it should be very opaque. And it turns out that the most dense form of matter you can make is transparent to light. And that was incredibly shocking to me. And you might have heard about things called neutrinos. And neutrinos go through everything, right? Neutrinos have an easy time going through matter, and you would think, well, neutrinos must have a pretty easy time going through one of the densest forms of matter there is in the universe. It turns out that's not true. If you go to very dense matter, you end up having material that is more opaque to photons than it is to neutrinos. And that just blew my mind. And I can see some of the other panelists having the same reaction.
Maybe I can comment. During my PhD, I worked in this project related to a strong field QED. Maybe you have heard one of the last two women winning the physics Nobel. One is related to lasers in physics. So if you use that technology, if you use lasers, in a laser, what you have are photons, are light particles of light. So if these photons have enough energy, and if you collide them, you can create matter out of light, matter out of energy, which is basically an insane famous equation, E equals mass and the velocity of light squared. So it shocked me that actually in one experiment at the Stanford Linear Accelerator, they were able to see for the first time in the 80s, I think, the creation of matter from light, which for me was, it was described at that time actually in the papers as magic, as how can you create matter out of light. For me, that was really amazing. And also some things related to dark matter, which I am very passionate about, just understanding something that you cannot see, but you see the very important effect on the galaxies, and actually understanding for me that galaxies and large scale structures, as you call clusters of galaxies, for example, wouldn't have formed without the existence of dark matter. That was also shocking for me. But yeah, maybe it's a bit abstract, but those two things I think were very impressive for me to learn.
So for me, two things I guess impressed me and were most, I wouldn't say surprising, but most impressed me the most in my career as a physicist. And they're both related to the work I'm doing right now, which is work with trapped ions and quantum computing. So the first was when I came to an ion trap lab basically for the first time and saw these glowing dots on the screen, which were actually images being taken at that time of single atoms, just single atoms trapped, suspended in space by electromagnetic fields. And the reason they were visible is because they a laser was shining on them, a laser of very specific wavelength, very specific frequency that made them very bright. So to me, that basically blew my mind that this is just even possible. And now I'm working with this, and my students are working with this every day. And the second thing is related to more of a quantum physics and more kind of deeper aspects of physics. That was when we were working on an experiment trying to generate entanglement. Entanglement is a very spooky, according to Einstein, quantum property of quantum particles. And so we were doing it in a specific, particular experiment. The entanglement has been demonstrated before in other systems. We were doing it in a different system, and for a long time, well, for months, we weren't able to see it. We weren't able to show that we have an entangled state. And then kind of, at some point it clicked. We realized what we were doing wrong, and basically just this one thing, we fixed it. We changed a tiny parameter in our experiment, and all of a sudden we saw these, the data. You look at the data, and if you don't know what you're looking at, it doesn't look like anything specific, but we knew what we were looking at, and the data showed entanglement. That was, proving Einstein wrong was kind of cool.
Okay, we have another question. Has COVID changed the physics industry right now? And if so, how? And what do you think it's going to look like even after it starts to go back to normal?
Well, I would say that we've been uploaded into the matrix and we only exist in Zoom now, in Microsoft Teams. So I know my last year has been nothing but Teams and Zoom meetings. But I think what it's really demonstrated is how far the technology's come to allow for remote collaboration, but I think it also points exactly where it's limited. And so what I learned is just how important in-person teamwork is with your other co-workers. And yes, you can jump onto Zoom real quick to try to replicate it, but it's not the same as being in the office and just bouncing a crazy idea off of someone, just off the cuff. And so I know personally, I cannot wait to get back to more standard operations. But I think it's also powerful that you can go anywhere on Earth and still work and still stay in touch. So very happy where pandemic in 2019 is much better than 1918. So I like that.
On the note of remote collaboration, I think one thing of a lot of bad things that has been helpful within COVID-19 physics is the amount of seminars that both I'm able to attend and my professors are able to attend is kind of crazy, because you can go to seminars at universities you would never have otherwise had any idea they were even hosting a cool speaker, and you can ask questions to people you never would have thought you'd be able to talk to, which has been really cool. But then also echoing Dr. Sutherland, I miss having a whiteboard and a chalkboard in my team's office so much. It definitely slows us down in a big way to not be able to just pull someone out of their workspace for a second and go over a problem quickly and then go back to your work. To just the act of having to schedule something has been different. That's not a large comment on the industry as a whole, but just in the day-to-day, more seminars, but harder to work on the day-to-day problems.
If I might say something, I think probably the conference and seminar part, some part of it will stay in the online way, because as it was said before, you can attend to seminars that there's no way that you could go. I mean, for example, this with a short notice, I was able to join, and if it wasn't because of this is online, it wouldn't have been possible. So I think some of that will stay, but it's true that it brings other challenges in terms of how you separate work life from your personal life, or your time to sleep, or your time to eat, because you're all the time in front of the computer, and sometimes it's very easy to just listen to a seminar or being on a meeting in which you're not the first contributor, which you don't have to show the results and you can be having lunch. It's easy to I don't know, merge in this matrix, as Derek said. I think it's difficult to separate different parts of your life, but yeah, and also I think it brings maybe more pressure sometimes, because instead of having meetings with your collaborators in one, I don't know, seminar room, or just have meetings every week, and every week you need to have something to show. You need to have results every time, and that means that if you have 5 different projects, you need to have 5 different results for every week. I think in that sense it's more stressful, but it has its advantages as being able to join this kind of events. But yeah, it has been difficult, but we will get out of this, I think.
Yeah, I think there are tools that we've discovered through this pandemic that we are going to use well past the pandemic. Hopefully, very soon we will be back in our offices doing science and talking to each other. One of the things that I felt these tools are still unable to provide us is the spontaneity. There is a lot of structure to meeting on the internet or meeting through these devices. It might just be because they are new to us and they feel unnatural. But as of now, I feel like most of the meetings, and this is something many of my colleagues share with me, most of the meetings are so structured there isn't time to say, okay, let's just shoot the breeze here and try to think about crazy stuff, which is what you do in your office talking to colleagues, and that's how new ideas come about. So I think that'll be nice to recapture when we get back to the office. But who knows, maybe there's a smart programmer sitting out there figuring out how to make that happen virtually as well. But we'll wait for that.
Okay, we have another question from the chat, and this is for any of the panelists can answer. So what is a mistake you made from your career, and what did you learn from it?
So one, I can say sometimes you're onto something interesting and there's just not a lot of excitement in the community. You find just a lack of enthusiasm for an idea that you think is cool. And when you're young, you tend to listen to the wiser people in the field. and that's not always a good thing. If you have an idea and you think it's interesting intrinsically, even if famous wise people tell you otherwise, don't be discouraged. And there are at least a couple of instances in my career where I gave up on an idea a little too soon. And then only to find somebody else had picked it up and done what I had thought I could have done, and it was really cool what those people did. And there's just a lack of that recognition when you're young, and that's something it's hard to learn, but you can do that retrospectively sometimes.
I think I can say not in my career because this is my first job. So during my formation, when I was in the university or in high school, not asking more questions or being afraid of asking more things or thinking that my question is stupid or silly or naive. I didn't go to university in this country, so at least I can talk only from my personal experience that many times it's considered that you are dumb because you're asking, or I don't know, that if you ask, people will judge you, but then you realize that a lot of people have the same question as you, or maybe not. Maybe it's only your curiosity, and that is enough, I think, to cover that only for you. So I think if I could go back in time, I would ask much more questions. I wouldn't listen when people would say, you're not going to understand because you're a woman, or you're not going to understand because, I don't know, you're South American or whatever. Just trying to learn more and just trying to ask more questions. That would be my lesson.
Personally, I think early on in my university years, I think it took me a while to realize that every time I asked for advice, the person I'm getting advice from was always coming from a very particular perspective. And I think it took me a while to contextualize all that advice and learn how to figure out for myself whether or not I agreed with it. And I think that's not necessarily specific to physics, but I think it would have been helpful to know going into university that, like, I'm going to hear a lot of things about what I should do, but I need to figure out if that's actually squares with what I want to do later on, and also thinking of where that advice is coming from, and if someone's trying to angle me towards a particular subfield that I don't actually might end up in.
All right, then let's end with the last question of this panel. And it's from one person who's really passionate about radio astronomy, and so they want your guys' advice. And so they're wondering, like, what university or what courses would you guys recommend? And also if if you guys recommend going to a non-US university, despite it being hard to get scholarships, stuff like that.
So I don't know a lot about different programs outside of the US in radio astronomy, but a good astronomy program should be your top choice. And then, if they have hopefully a good astronomy program in the US, we'll also have a strong radio astronomy program. Radio astronomy has and continues to be an incredibly powerful tool. Some of the greatest discoveries in both on large scale galactic structure come from radio astronomy, but also in my own area of research, which is pulsars. Radio astronomy has been basically fundamental. There was one Nobel Prize for radio astronomers to have discovered the first binary neutron star, and discovered actually before gravitational waves, that gravitational waves were being emitted before the direct detection of gravitational waves, realization that gravitational waves were being emitted by binary neutron star system. So it continues to be a very exciting field. And my advice is go to a university that doesn't only specialize in one type of astronomy. Go to a program that has breadth, and that will turn out to be very important, because the kind of questions radio astronomy will ask in the future are certainly going to come from many parts of physics, cosmology, and astrophysics. So having that awareness is going to be critical.
I would also say, I think there was a question regarding schools outside of the US. So when I was applying to grad school in particular, I was looking abroad as well. So I came down to going to the Max Planck Institute in Germany, or staying in the US and doing that. And what I found is that the educational systems are a bit different in Europe versus the US. So like, for example, in Europe, it's more typical for you to do a master's first and then do your PhD. Whereas in the US, it's if you're going to do a master's, you can do the same thing, but you can also just go directly to your PhD from your bachelor's. And so that's what I ended up doing in the US, but that's less typical in Europe. So you just have to kind of pay attention to what are the requirements and how does your education, wherever you're at, translate into the country you're looking to apply to. Yeah.
I don't know specifically about good universities to study radio astronomy, but what I can say is that there are always summer programs for undergraduate students. I don't know if there are summer programs for high school students, but there are resources, and you can look, for example, in the different observatories. Sometimes they have special, I don't know, workshops or small things where you can get information more specifically about what you want. So maybe that will be also informative.
All right, thank you for your response. And that concludes the Q&A. Thank you all so much for coming today. Thank you to all of our panelists. Thank you to our moderators and everyone who helped make this happen. To our attendees, you are encouraged to consider coming to other panels the rest of the week. You can join from the links on our website. Also, in the chat is an after-event survey. Please fill this out. We value your feedback. Thank you, everyone, and that concludes STEM Fair.
Thank you for the invitation.
Yeah,
This was
Bye, and good luck.